Math 2415, Calculus 3, Multivariable Calculus, Chapter 10, Vectors in the Geometry of Space, Section 8, Arc Length and Curvature, Video 1, Arc Length from 2 to 3 dimensions. We're not going to do an example in this video. We're just going to get the formula out there. But first, let's review what we learned in Calculus 2 about arc length. We actually learned it from two perspectives, rectangularly and parametrically. Rectangularly, that just means we have a function y equals f of x over some closed interval from a to b, where we have a little illustration here. And the arc length, the arc length is calculated as the integral from a to b of the square root of 1 plus the square of the derivative dx. And you may recall from Calculus 2 that sometimes this can get pretty ugly because of the integrand being the square root of a sum. Sometimes these functions are chosen nicely so that the integral will behave. Sometimes it doesn't behave very well. In the event that you get something that is unintegrable, you can use a technique to approximate the definite integral. But in space, we don't define curves as functions of x and y. Z is a function of x and y. That would actually give us a surface. We define them parametrically. So reviewing how to do the two-dimensional arc length parametrically, let's say we have a curve defined parametrically by x equals f of t and y equals g of t over a closed interval ab. I neglected to mention back here that this is well defined as long as the derivative is continuous, because to integrate a function, it only needs to be continuous. So as long as the derivative of the function is continuous over the interval a to b, we're good. Same thing here, as long as the derivatives of f and g are continuous over this interval, we're okay. But as long as the parametrization of the curve doesn't retrace it, and by that, I mean, for example, if we had a circle and it got traced again, and then it came over here and then traced again, anything that retraces will not accurately calculate the arc length unless you take into consideration how many times it's retraced. But we simply won't worry about that. All right, so the arc length is the integral from a to b of the square root of the sum of the squares of the derivatives of the component function. So f prime of t, g prime of t, and then dt. This stemmed from using the distance formula and approximating the curve as a sequence of approximately linear line segments, and then doing a Riemann sum, taking a limit. So how do we bump this up to 3 dimensions? Well, honestly, we just stick in a third component function. In 3 dimensions, a curve defined parametrically is x equals f of t, y equals g of t, z equals h of t over the closed interval a to b. As long as the curve retraces if the curve is traversed no more than once. And I also forgot to mention back here that when we define curves parametrically, excuse me, my brain's not firing in all cylinders today. There is an orientation, a direction, if you will. And so this curve is traced out from the value of t equals a to t equals b. Similarly, on the space curve, all we have to do is modify the integrand so that under the square root, we have 3 add-ins. The square of the derivative of the z component function. So it would be the integral from a to b of the square root of the derivative of f of t squared plus the derivative of g of t squared plus the derivative of h of t squared dt. And on a higher level, this can be extended to as many dimensions as we want. If we had a 20-dimensional curve with 20 component functions, we could calculate its arc length, whatever that would mean, by simply having the square root of the sum of the squares of the derivatives of all 20 component functions. Now, before I wrap up this video, I do want to point out that this can be thought of in vector form. In vector form, we're going to start by letting a vector function r of t have component functions f of t, g of t, and h of t. I want to remind you that normally I would draw an arrow over everything that represents a vector. Well, I guess I'll go ahead and do it there. Then if you go back and think about what the integrand is, it's the sum of it's the square root of the sum of the squares of something, which reeks of magnitude. Magnitude is the sum of the magnitude is the square root of the sum of the squares of the component function. But in this arc length formula, it's the squares of these guys. So who has f prime, g prime, and h prime as their component functions? And the answer is the derivative of r. So in other words, we could calculate our arc length by saying the integral from a to b of the magnitude of the derivative of r. And so this kind of summarizes it pretty straightforward. This can also be thought of as a speed formula if r is measuring a position, because the derivative would be the velocity and the magnitude of velocity is speed, but let's not get too in depth into that right now.